Okay, several people asked me if I could work through an example of a Born-Haber cycle, so especially for something more complicated. So I'm going to do a Born-Haber cycle for calcium nitride, which has the formula Ca3N2. So when you're doing a Born-Haber cycle, the way I like to break it down is you write the ionic compound here, and then you have the reaction here that would form it from elements in its standard state, so the delta H of formation. So we would have 3 calcium atoms plus a molecule of nitrogen gas to form this calcium nitride. So going this way, this would be our delta H of formation. Now in the upper left-hand corner, we have to do whatever it takes here to get to gaseous atoms. So for calcium, we'd want 3 calcium atoms, but now we want them to be gaseous. The reason being, when we do ionization energies and electron affinities, those are always calculated for gaseous atoms. So we have to make them that way. Nitrogen is already a gas, but this is a nitrogen molecule, not nitrogen atoms. When it comes up here, we're going to actually have 2 nitrogen gas atoms. So how do we get from the solid to the gas? In this case, for calcium, we would need the delta H of sublimation for calcium, and we would actually need 3 of those. Why? Because we have 3 moles here of calcium and 3 moles of calcium gas. So we need 3 times the normal delta H of sublimation, which would be for 1 mole. How do we get from nitrogen to nitrogen atoms? To do that, we're going to have to break the nitrogen triple bond in the nitrogen molecule. So now that we have gaseous atoms, in the upper right-hand corner, I like to write gaseous ions. So here we'll have 3 calcium 2+ ions and 2 nitrogen 3- ions. Of course, this process going down from the gaseous ions to the ionic compound is what we call the lattice energy. And now how do we get from here to here? Turns out calcium, each of these calcium atoms is going to have to lose 2 electrons. So we're going to need the first ionization energy and the second ionization energy to remove 1 and 2 electrons for calcium. And because we have 3 atoms or 3 moles of calcium here, we'll need to actually multiply these times 3. And how do we get our nitrogen atoms to become nitrogen ions? Each of these has to actually gain 3 electrons. So we're going to need the first electron affinity and the second electron affinity and the third electron affinity for adding 1, 2, 3 electrons. And we have 2 moles of those nitrogen atoms, so I'm going to need 2 of all of those. So now, if I wanted to solve for the lattice energy, assuming that I have all of this other information, which is the most common situation, let's see. I'm going to make a pathway, sorry for the delay. I'm going to make a pathway that goes like this. So I'm going to call this one minus the lattice energy. And then my other pathway starts at the same place over here, but it's going to go all the way around like this. And I'm going to add all these things up. If I'm going backwards this way, obviously then this becomes negative delta HF. Okay, so I'm going to now make my equation. I have minus LE, which is my first pathway. Because of Hess's law, we're able to equate 2 different pathways because we know they start and end at the same place. And the enthalpy is a state function, so it doesn't matter which path you take. So we're able to equate this path and this other path. Why would somebody do this, you ask? The reason is we don't normally have gaseous ions floating around, and so it's actually difficult to figure out what this lattice energy is. On the other hand, we know very well what the delta H of formation is. All of these other things are easier to measure. And so it's common for us to know those values but not know the lattice energy. Okay, so I would say the negative lattice energy, which is my first path, equals my second path. I'm going to go all the way around. So I have negative delta HF. As a note, delta HFs are frequently negative themselves, so you may actually end up now by having the opposite of the delta HF with a positive number here. And now I'm going to add these on. 3 times the delta H of sublimation for calcium. The bond enthalpy for nitrogen. 3 times the first ionization energy of calcium plus the second ionization energy of calcium, so we can get those +2 ions, and we need 3 of them. And then 2 of our electron affinities for nitrogen, all 3 electron affinities. We need 3 of them because it becomes a 3- ion. We need 2 of this whole quantity because we have 2 moles of each of those. So now, assuming that I know all of these quantities, I just plug them in and I solve for the lattice energy. Things to watch out for here basically have to do with counting. So you want to be careful about how many moles of each thing you have. So see how I have the 3 moles of calcium? Well, then I need to multiply my delta H of sublimation by 3. And then the other thing that you want to watch out for is up here when you're going from an atom to an ion, be careful that you include all of the information you need. So calcium loses 2 electrons, so I need both of those ionization energies. In any case, this should summarize a Bohr-Haber cycle. We start with our elements in their standard states. We have our ionic compound here, and then we make this sort of artificial path going to gaseous atoms, gaseous ions, and then we just equate these 2 paths using Hess's law. The other way that you can do this, if you don't like drawing all of this stuff out, is you can actually write out all of the equations the same way you would with Hess's law when you took Chem 105. So, for example, you could have the delta H of formation equation. So you could have Ca3N2 solid and 3Ca plus N2 gas. That's your delta H of formation. And then, so we want to have this over here, but we don't want these guys. We want to end up having our ions instead. So how do we take these now and turn them into ions? We just do all of these things that we just did. My 3 calcium 3 calcium atoms that I want to have. That's going to cancel out my 3 calcium solids, right? So I'll have 3 calcium atoms, gaseous atoms, and this is going to be -3 times the delta H of sublimation for calcium. And we would do something for nitrogen. We want to get rid of nitrogen on this side instead. We want to have the atoms of nitrogen, so 2 nitrogen atoms, making N2 gas. And this would again be the bond enthalpy, the opposite of the bond enthalpy. Here I'm basically taking the opposite pathway around the circle, so that's how this ends up happening this way. So now my nitrogen gas will go away, but now I've got atoms and I want to get ions over here. So to get my 3 calcium ions from atoms here, again, now I need the opposite of 3 times the ionization energies for calcium. So you can continue this way I don't know whether you want me to continue this way. I'll just finish it out. We'll end up here with 2 N3 minus gas coming from 2 N gas. How do we do this? This is going to be 2 times the electron affinity 1, 2, and 3. And when we add up all of these things now, our overall equation, which is just barely going to fit on the bottom here, is going to be 3 Ca2 plus gas plus 2 N3 minus gas makes Ca3 N2 solid, and this is actually the lattice energy equation. That's how it's defined, as going from the gaseous ions to the solid ionic compound. And so if we added up all of these things, we would get the lattice energy. Notice this is exactly the same as what we have written here, except all the signs are opposite. So it's 2 different ways to do a Born-Haber cycle. Either one of them is acceptable. I prefer this sort of graphical method because it helps me keep track of things. Sometimes if you're doing this, it can get confusing and you might not remember all of the pieces that you need. So there you go. That's a Born-Haber cycle.